middle value, say 100 ohm, okay? And then there's some variation around this 100 ohm. Let's say 5%, give us what, 95 to what, say 105 ohm. In other words, the measurements might vary between 95 to 105. Okay, obviously this is a number, right? And here this is what? Symbols. And a random variable can be used to represent all those events. We all end up having actual numbers. Okay? So that's what random variables do. So basically, what is random variable? Well, it's a mapping actually. On the left side, we have a sample space. Right, associated with one specific experiment. For example, if we flip a coin, right, the sample space will be just like, say, H and T, right? If we measure a resistor, then it could be the value between what? 95, for example, 105, right? This is our sample space. And then random variable is a mapping here, which maps this sample space into a subset of the real number. So this is a real number here. Could be from minus infinity to infinity. Okay? So obviously, for different sample space, we might use different subsets of a real number. So somewhere here. Okay? And obviously now you can see here, we end up having actual numbers. All right? And for example, if we use this mappings, so-called uppercase X here, and this, for example here, if we have this sample space, for example here, we might generate the following random variable, like say here, X, H here. We map this event to what? Say 0. Okay? And we can map tail to 1. So now you can see here, this X represents the random number, random variable associated with flipping coin experiment. But now we can represent event head with number. In other words, if we say X equal to 0, this will be equivalent to what? Head event. Similarly, X equal to 1 equivalent to what? Tail. Okay, in other words, now we have these two numbers. That's 0 here, and then 1. These two numbers, just two numbers. Okay? And we call X is random variable, right? And the 0 and 1 are two specific realizations. All right? And now we can describe the probability as follows. Say probability, like say X equal to 0, equal to what? Half, right? And then the probability X equal to 1 equal to what? Half. Okay? So because we just mentioned, right now this equation actually, this equality represents event head, and this represents what? Event tail. Okay? So in other words, we are going to use numbers, equations, or inequality to represent actually different events. Yes?
So, but there's a difference between the heads and tails and then the 95 to 105 because there's only two options.
Oh, no,
there.
that's different
Oh, it's different.
story.
Oh,
So
okay.
I just mentioned for different experiment, there's different sample space.
Okay.
Then we are going to have different result of the mapping, right? And for this flipping a coin experiment, we map head to 0. We map tail to 1. And even this mapping could have multiple options. For example, we have freedom to say map head to what? 10. We can map tail to what? -10. Any options would be allowed. But we just need to know this one-to-one relationship between, head with the corresponding realization, tail and the corresponding realization. No matter which option will be used, it's always true that, say, px equal to 10 will be same as what? The probability of what? H. Okay? It will be equal to what? The probability x equal to 0 for this option here. Okay? So in other words, after we build this mapping, we just need to stick to this mapping here. Okay? And for the second example, okay? Because the measurement already is a number, right? Then we can just say, okay, map this interval. Okay, let me separate here. So resistor between 95 to 105. Theoretically measured to what? Say 95 to 105. Okay, and if we call this theoretically say R, okay, represent this random variable, right? And then we can represent the probability like this, R, like say between, like say 98 to 99, for example. Okay, this type of probability. Okay, and of course it's still, we need to study a little bit more advanced concept later before we can figure out this type of probability. Okay, but here you can see here, this is already number, so we can directly map this number to the same interval on this real number axis like this. Okay, so let's have one more example. Say this experiment. Okay, this is a new experiment we touch on. Let's say the experiment is about spinning a relay wheel. Okay, so we can see different relay wheels in Las Vegas, right? And here, spinning a relay wheel, and then it will be mapped to what? A number between, say, 0 and 1. Okay? And this is the experiment. As a result, the sample space will be what? The number between what?
0,
0 and 1. And also, just like the resistor measurement, we also map this guy to the interval between what? 0 and 1. Okay, let's also call this x here. Okay, but here, this is what? This will be between 0 and 1. All the numbers between 0 and 1. Okay, somehow you can see here, for example, for this experiment, the random numbers you can see here are what? Are called discrete because there are only two possibilities, 0 and 1, for example. But here, this random number can take on infinitely many values between what? 0 and 1, right? In other words, the sample space will be what? Will be between 0 and 1, right? So in other words, at least now we know the sample space, the probability when x between 0 and 1 should be what? Should be 1, right? And also if we know, say, A is greater than 0, less than 1, and B is greater than A but less than 1. In this case, x between, say, A and B. And because basically when we spin such a relay, the chance that it would stop anywhere will be uniform. In other words, it could be anywhere between 0 and 1 uniformly. So that's the reason why we can say the probability will be what? B minus A. The length between these two numbers. Okay? And basically, you can say this is called, like in this case, discrete random variables. Okay? And this is the case what? Continuous random variables. Okay? So these are two categories we need to deal with. All right? When we study probability. And then later, let's say, when we study random signal processing, okay? Just like the difference between 350 and 351, we can talk about, say, continuous random signal processing. And then we can also talk about discrete random signal processing, all right? So now, we just mentioned random variables can be defined as a mapping from the sample space to a subset of real numbers. All right. Now the question is, how can we characterize, these random numbers? In other words, how can we build a model so we can represent, like say, the chance a specific number would become a realization? What's the chance of 0? What's the chance of 1? What's the chance that this guy will be between, say, 0.2 to 0.5? Okay. In other words, how can we determine probabilities? And in order to build such a model, we need to define a special function. So this function is called probability distribution function. All right, so now let's say this is just a flip a coin, right? Flip a coin. So sample space is HT mapped to, let's use this mapping here, just 0, 1, okay? And this is the relay experiment mapped to 0, 1, okay? And we are going to talk about how we can build distribution functions for both experiments. And then we are going to see the difference between discrete random variable and continuous random variable in terms of what? Distribution function, okay? So we give a definition first. So what is the probability distribution function? And this function actually represents the probability of a specific event here, uppercase F here, and then this subscript uppercase represents random variable, okay? And inside, the independent variable actually represents specific realizations. Just like here, this is a random variable, uppercase, right? And the realizations are what? 0 and 1. Okay? And here, this is a random variable, right? And the specific realization could be anywhere inside the interval between 0 and 1. Okay? And then this function is defined as a probability when this random variable less or equal to a specific realization, which is what? Which is the corresponding independent variable of this function. Okay? So this is the definition for the probability distribution function. Okay? You can see here, now, after we build such a mapping from sample space of experiment to specific real numbers, right? Then we can use, like, for example, inequality to represent different events, okay? Because keep in mind here, for example, in this case, you can see here, the sample space is what? Between 0 and 1, right? remember the definition of event. What is event? Event is a subset of sample space. Okay? So now you can see here, any subset of this interval can be used to represent what? Any event. And here, that's the reason why you can see here, this is just one of those events. This inequality means the realization should be between what? A and B. Okay? Specifically, it could be like this. X between what? Say 0.1, 0.3, for example, right? So this is just one of infinitely many possible events. Okay? And here, remember, so far, actually, we focus most of the time on actually finite sample space, right? For example, this type of sample space. Okay, and then the number of subsets will be finite, right? Because we know if you have, like, say, n outcomes elements in your sample space, then the total number of subsets will be what? 2 raised to n, right? But for this continuous random variable, obviously, the number of subsets will be what? Infinity, right? That's the difference. Okay, so now, let's try to build this probability distribution function for both random variables. Okay. And here you see here because this random variable uppercase x has only 2 realizations, 0 and 1, right? And when we try to build such distribution function, we have to consider all the possibilities in terms of range of x here. For example, here, we may decide like this: x less than -1. Okay, right here, because the possibility is like this: 0 and 1, right? Oh, okay, sorry. Actually, in this case, I changed a little bit. You can see we change it to say -1 to 1. Okay. In other words, -1 for tail and 1 for h. Okay. So you see, we just have freedom, to pick up any possible values for the respective outcomes. Okay, and then now you can see here, we already know, based on this mapping, we know, let's say px equal to -1 will be equal to p tail, right? Equal to half. Similarly, probability of x equal to 1 corresponds to what? Hat equal to what? Also half, right? So these are 2 possible, outcomes here. Okay. So -1 corresponds to tail, 1 corresponds to hat. And then now, here, this is a function of the realization of random variable, right? And here, this function x should be defined anywhere. In other words, could be anywhere in the real number axis. So, and here, because you can see here, at different values, they take different probabilities. So we have to, let's say, consider different possibilities. Like here, for example, case 1, when the realization is less than -1. Okay, so in other words, it will be here. It will be here, x here. Okay, and then what's the corresponding value of this distribution function? And here, this represents what? When this random variable less equal to realization, and the realization is here, right? So you see here, it's what? It's something like this. So this is the corresponding event, which means this is what? Right? So this inequality corresponds to this direction here, right? Less or equal to what? This specific realization. And here we just put constraint on the value of this realization, which is what? less than -1, right? Okay, now, on this constraint, x is less than -1, what's this probability? Is what?
0.
0, because obviously inside this range here, it doesn't include either head or tail, right? Because tail corresponds to what? -1. Head is what? 1. And this interval does not include any of them. In other words, the probability is what? 0, right? Okay? So you can see here, we still need to kind of like go back to the basic event concept we learned before, right? Gradually, of course, we are going to focus on just, numbers. But at this early stage, we have to still, let's say, interpret this inequality in terms of what? Basic events, we learned before, okay? So this is the first case. Second case, when this realization, okay, is between what? Could be large equal to 1, but less than 1. Less than 1. And then now, in this case, you can see here, -1, 1, 0. Okay? Let's not label this 0 here because it's not so important for us. So let's just say, okay, x is somewhere here. All right? You can see here, -1 might be inclusive, but 1 should be, exclusive. And then now, again, we have to determine, this probability here. So we should be what? Like this, right? Okay? So now you can see here, this interval actually represents this new inequality here. And obviously this guy includes what? -1. This point, this one point. In other words, this just same as what? Same as the probability x equal to what? -1, right? Because the probability will be 0 anywhere else except what? -1 here. So as a result, this should be what? 0.5, right? 0.5. Yes?
Is it because it's a discrete and there's no other options?
That's right. And here, this probability only defined at 2 positions. -1 for tail, which is what? Half. And 1 for head, which is also what? Half. And here, this inequality, you can see here, obviously only includes what? -1, this position. That's the reason why this probably should be what? 0.5, right? Okay? And this is case number 2. How about case number 3? When x is larger or equal to 1, okay? In this case, you can see here, so x should be somewhere here, right? And then this inequality, this represents what? Random variable is less or equal to realization here. Okay. So now, what's the corresponding probability for this event?
1.
1. Because this inequality actually includes what? Both -1 and 1. In other words, this will become the probability of the sample space, which includes what? Both -1 and 1. Okay, that's the reason why the probability should be what in this case? Is 1. Okay? Now if we draw this function for something like this. Alright? And here this horizontal axis, hold on, represents the realization value of a random variable. Small x here. Keep in mind here, I just keep emphasizing, the difference between uppercase and lowercase. And here, uppercase represents what? Random variable. And lowercase represents what? The corresponding realization. realization could be, like say, the number of realization would vary greatly among different experiments. In this case, it's just what? 2 realizations, right? One, -1 and 1. And if we draw this function here, we have to pay attention to 2 special values, which is what? -1 and 1, right? Probably it's better to use different colors. So based on first condition here, when realization is less than -1, this function actually, this is what? This function is 0. And keep in mind here, this function represents this probability. So in other words, this will be 0, right? Okay. When x realization is less than 1, it will be 0 value here, right? The vertical actually just what? Distribution function here. And in the second case, when realization between -1 and 1, the probability become what?
0.5.
0.5. So which means if this is 0.5 here, so it will be a jump here. Like here, this is what? 0.5. Okay? And then when x realization is greater or equal to 1, it becomes what? 1, right? So it's 1 here. Should be 1 anywhere. And this would be the probability distribution function associated with this flipping a fair coin experiment. Okay? And also pay attention here, you can see here. This function obviously is what? Is discontinuous, right? There's 2 discontinuity points at the -1 and 1. So, and here it jumps from 0 to what? 0.5. And here jumps from where?
0.5
to 0.5 to 1. Okay? And also you can see here, it's an increasing function. You can see here, it's increasing. Okay? And also you can see here, what's the value of this function at infinity?
1.
You can see it's 1, right? It's 1. So what's the value of the function at the minus infinity?
0.
0, right? Okay? And because this function represents a probability, there's no wonder this function should be always what? Between 0 and 1, right? Because it's a probability. Okay? We cannot, the function cannot be beyond this range. It must be only between 0 and 1. And also you can see here, this is what? Increasing, right? The function increasing. Okay? So you can see here, anywhere here, you see here, for example here, if this is x1, x2, in other words, when x1 is less or equal to x2, then fx1 should be what? Less or equal to x2. So that's the meaning of increasing, right? Of course, increasing includes this special case, let's say, equal to each other, right? But here you can see here, this is what? x3. Now you can see here, fx3 larger than what? fx2. Yeah, question?
I was just wondering if you could explain why for case 3, it's not shaded on the opposite side?
So okay, here. So this is the location of this realization. You can see here, in this case, x is what? Greater or equal to 1, right? And then this inequality just includes what? Both 1 and -1. These 2 special positions. As a result, this probability just equal to what? The probability of the sample space. 1 minus 1. That's the reason why it must be what? 1, right? Okay? Yes?
Just to add on to that, how do you, because I know you did the probability that x is equal to -1.
Mm-hmm.
How do you do the probability that x is equal to 1? Because that is also 0.5. How would you do
Okay,
that?
yeah. So actually that's a good question, because actually we are going to find out for discrete random variable, actually, it's very important just for us to define, all the possibilities at discrete possibilities, discrete values like minus or 1. And we can call them, let's say, point mass function. Okay. And if we know this point mass function, then all these statistical values can be derived from those PMF functions. Okay. So in other words, somehow it's more important for us to focus on these point mass functions for discrete random variables. On the other hand, for continuous, all right, then this distribution function will be more useful. Okay. In other words, yeah, it's okay if we only focus on these point mass functions. So later we're going to see, like say, in order to determine the mean value and the variance, and then the calculation will be totally different between discrete random variables and continuous random variables. Okay? All right, and here at this early stage, we just try to see the difference between discrete and continuous in terms of, the difference between their distribution functions. Okay, we're going to talk more regarding, how to deal with discrete random variable and continuous in separate approach. Okay, so now let's talk about how to build a distribution function for this continuous random variable. Okay.
Professor,
Yes.
before you move on,
Yeah, go ahead.
I'm still really confused on the third case.
Okay.
I understand that x is greater than or equal to 1,
Right.
but I don't understand how x being less than x, just like the previous examples, makes us refer to only what's behind.
Okay. And in order to avoid all the confusion here, we need to understand the meaning of uppercase and lowercase, right? We just mentioned uppercase here represents what? Random variable. It's random, right? And we know, just like the outcome could be either head or tail. And here, this random variable could be either -1 or 1, right? And then -1 or 1 would be two possible realizations, okay? And meanwhile, and here, even though this experiment has only two possible realizations, but when we define function, we have to take off all the values on the real-time axis. All right? So reason why we have to divide, the values of realization into three different cases is we just take into account the situation like say these two special points, their locations. Okay? So in other words, we have to say, okay, when the realization is on the left side of -1, so this first case, right? When the realization is between these two, points, -1 or 1, case number 2. Case number 3, when the realization is on the right side of 1, so which is here. Okay? Because the reason why is we have to determine the function value at any position in the real-time axis. So that's the reason why, okay, we have to figure out all the possibilities. And the number of possibilities just depends on what? Your sample space.
So just to be clear, the x to the right of the number 3, that's a lowercase x, right?
Oh, you mean here?
Yes.
And this is uppercase,
Okay.
uppercase. And this is lowercase.
And to the left of that, that's a lowercase x.
Oh, that's right. That's right. This is lowercase. Lowercase actually represents realization, right? So when the realization is on the right side here, okay, and this represents what? This event. When this, in plain language, it represents what? When the random variable less or equal to this specific realization. Okay, here. Okay. Any other questions?
And the random variable is pretty much a variable that represents all of the whole sample space pretty much?
Random variable just represents, you can say, the outcome of the experiment.
Okay.
Now you can see here why it's random, right? Because the outcome will be random. The difference is we used to use symbols to represent the outcome. And here we use what? Numbers to represent the outcome. That's the difference. And after we define random variable, then we can define what? These functions. Otherwise, we cannot define functions. Okay? Because modeling basically is about build different type of functions. Okay? Especially later, we are going to talk about, say, Gaussian distribution, special function. We are going to see Gaussian distribution would allow us to build, all kinds of models in different fields. Especially for us, electrical engineering, you see here, like say, we can build our communication system based on what? Gaussian distribution. Okay? And then we can also say we can build a communication system based on different distribution. So that you're going to see the importance of those functions. Okay? All right, so this is the, of course, at the very beginning, those concepts might feel confused. So hopefully, gradually, we can clear our doubts. Okay, we will become more comfortable. Okay. For the second example, this is a continuous random variable, right? And here you can see here the sample space is between 0 to 1. If we draw this here, 0 to 1, right? Now, just mimic what we did on the left side. Just imagine, how many cases do we need to consider when we try to build the distribution function for this experiment?
Infinite?
How many possibilities in terms of realization location?
Three,
right.
Regions, yeah.
So just like, because the range is 0, 1, right? So you can see here, okay, let's also use different colors. Probably the first case should be what? When the realization on the left side, right, of 0, okay? And the second case, when the realization is between 0 and 1, right? Somewhere here. Case number 3. When the realization is on the right side of 1. Okay? And for each of these 3 cases, our goal is to determine what? The corresponding probability. Right? And here, what's this probability here? Case 1, this is our event, right? What's the corresponding probability in this case?
0.
0. Because obviously, this is not a subset of our sample space. Because sample space must be between what? 0 to 1. Okay? So as a result, this is what? 0. Okay? And then, for this event, second case, what's the probability in this case? Keep in mind here, how can we determine this probability? Because that's how we can determine probability, right? So obviously, here, this represents an event, right? But the sample space is only between 0 and 1, right? We have to determine the intersection between this event and the sample space, which should be what? Where?
Probability between 0
right.
and x.
This part, right? So this is the intersection between this event and the sample space. In other words, this will be equivalent to what? The probability when random variable between what? 0 and the lowercase x. Right? Doesn't it make sense? Which is what? This one here. Right point minus what? Left point. X here, right? Okay? case number 3. And the event is this guy here, right? Again, we have to determine the intersection between this event and the sample space, which should be what? What's the result of this intersection? This should be
X
what?
minus 1.
0 to 1, right? Because here it's about what? The intersection between 0 to 1 and minus infinity to x, right? So this corresponds to this inequality here. Okay, and here because x is on the right side of 1, so obviously this intersection equal to what? 0 to 1, right? Does that make sense? Okay? So in other words, in this case, equal to what? Which is what? Sample space. It's what? It's 1. Okay? Because the key is here you have to keep in mind, what's the sample space? Because any value, outside of sample space would be 0, probability-wise. Okay? For example, in this case, and here our samples is here, right? And the intersection will be what in this case? Because this inequality always, let's say, minus infinity to x, right? Intersection with what? 0, 1. In this is what? Empty. So no wonder the probability is what? Is 0 here. Second case. You can see here when x is here, what's the intersection? 0 and x. So that's why it's this probability. And here is what? Last case is 0, 1. Okay? And we can also draw this distribution function. Here, horizontal represents realization, right? And this is a distribution function here. Okay. So now you can see here, this is 0. Okay. When this is what? This is corresponding to x is less than 1, right? Less than 0. Sorry. Case number 1. Number 2 is when x is between 0 and 1. Okay, case number 2. Case number 2. Case number 3 here is what? When x is greater or equal to 1 here. So you can see here when x is less than 0, the distribution function is what? Is 0. So it will be like this. 0, 0, 0, 0, 0, 0, 0. Okay? And then when x becomes 1, it should be 1 here. So in other words, it should be here. So this line actually corresponds to what? Function is x, right? A linear function x. And when x is larger than 1, it will be what?
1.
1. Okay. Okay? So this will be the corresponding probability distribution function associated with this, Roulet experiment. And also, this is a distribution function for a continuous random variable. Okay. Also, we can easily verify, like in this case, the function value, say, should equal to what?
0.
0, right? It's the same as discrete. And they share the same property, right? How about value at infinity?
1.
It's 1. Okay? And also, it's increasing. In other words, if x1 less or equal to x2, then the value at x1 should be what? Less or equal to what? x2. Right? Okay. Of course, again, this function is what? Between 0 and 1, right? Okay. Yes.
So I'm kind of confused on your notation when you do the intersection between the two.
Right.
So the way you do that is by intersecting the sample space with wherever your realization is.
And this represents our inequality here. And this inequality, like say, basically you can put minus infinity on the left side. Okay, that's you have this minus infinity on the left side. Realization on the right side. So this is the same as this inequality here. Okay? So just for example, if you say, maybe space now may make more sense. So this is what? Minus infinity 2, right?
Okay.
If you say x large equal to 2, it would be what? 2 infinity. You can include, infinity at the right side. Okay?
So for the top one, shouldn't it just be negative infinity to x intersect with 0? Because it doesn't intersect with.
Right, that's empty, right? So see here, that's empty. Intersection is empty. There's no overlapping between these two intervals. In other words, no overlapping means no intersection. Result is empty set.
Okay.
Okay? And or this is what? Null event, right? Okay? All right, so you see here, we just use these two examples, one for discrete and second for continuous, to demonstrate, all right, how we can build probability distribution function. And also we talk about some properties, which should be shared by all distribution functions. And here, let me ask you a question. Take a look here. The function is defined as this probability, right? What if we'd like to determine this probability? What should we do? Just think about this, okay? We'll talk about after break, okay?
Is it a break?